new Mars images reveal a strange mystery. October 3rd, 2025. Mars hangs in the cosmic void, separated from Earth by 250 million kilometers and the burning mass of our Sun. On this day, something extraordinary happens that no human eye can witness directly. Above the rust-colored horizons of the red planet, mechanical sentinels drift through the thin atmosphere, their digital sensors awakening to capture what may be the most important images of our generation. You're about to discover what they saw, and more importantly, what certain agencies don't want you to know about it. While Earth spins in ignorant bliss on the opposite side of our solar system, Mars becomes humanity's only window into an event that challenges everything we thought we knew about visitors from beyond our solar neighborhood. The interstellar wanderer known as 3I Atlas makes its closest approach to the red planet today, and for the first time in human history, we have eyes positioned to watch an alien world encounter an alien visitor. But here's where the story becomes strange. The European Space Agency had been planning this observation for weeks. Their Mars Express and ExoMars Trace Gas Orbiter had been positioned with surgical precision, their instruments calibrated and ready. NASA's fleet of Martian robots stood at attention, cameras pointed skyward. Everything was prepared for what should have been a moment of unprecedented scientific revelation. Yet, as the hours tick by on October 3rd, something unsettling emerges from the silence. While sophisticated spacecraft worth billions of dollars capture potentially groundbreaking footage of an interstellar object at closer range than ever before achieved, the flow of information to the public slows to a mysterious trickle. The timing couldn't be more perfect for observation, or more convenient for concealment. Mars orbits in a unique position today, offering vantage points that Earth-based telescopes could only dream of. The red planet sits like a cosmic lighthouse, illuminating secrets that our home world cannot see. Its mechanical inhabitants, rovers, orbiters, and landers represent humanity's extended senses, reaching across the void to touch the untouchable. But what happens when those extended senses see something that challenges our fundamental understanding of what's possible? What happens when the images they capture reveal truths that some would prefer remain hidden? As October 3rd unfolds in Martian time, a different kind of story begins to emerge. Not the sterile press releases of space agencies or the measured statements of institutional science, but something more raw, more human, and infinitely more compelling. It's the story of what happens when amateur astronomers refuse to accept official silence, when individual curiosity collides with institutional control, and when the truth finds a way to surface despite every attempt to manage its revelation. The mechanical eyes above Mars blink in the solar wind, their lenses focused on a speck of light that has traveled farther than human imagination can truly grasp. This speck carries within its frozen nucleus the chemical signatures of stellar nurseries beyond our Sun, the gravitational memories of alien solar systems, and perhaps the keys to understanding our place in a cosmos far stranger than we've dared to admit. Today, Mars watches what Earth cannot see. Today, the red planet becomes humanity's witness to something unprecedented. And today, the careful dance between discovery and disclosure begins to reveal cracks that will change everything. You're not just watching the story of an interstellar visitor making its closest approach to Mars. You're witnessing the moment when the controlled narrative of space exploration meets the unstoppable force of human curiosity. You're seeing what happens when the universe refuses to cooperate with carefully managed information campaigns. The images being captured above Mars in these very hours contain secrets that will ripple through astronomy, physics, and our understanding of life itself. But getting those images, understanding what they mean, and learning why certain organizations seem reluctant to share them immediately, that's where our real journey begins. October 3rd, 2025 marks more than just the closest approach of 3I Atlas to Mars. It marks the beginning of a revelation that will unfold in the coming days and weeks, piece by carefully hidden piece. The red planet has become our window into cosmic truth, and what it shows us will challenge everything we thought we knew about visitors from the stars. The mechanical watchers above Mars have seen something extraordinary today. The question is, when will they tell us what it was? And perhaps more importantly, will they tell us everything? In the darkness above Mars, two mechanical sentinels drift through their programmed orbits, their instruments humming with electric anticipation. Mars Express and ExoMars Trace Gas Orbiter represent the European Space Agency's most sophisticated eyes in Martian space, and today they have been tasked with something unprecedented in the history of space exploration. Between 1 and the 7th of October, our Mars orbiters will observe the comet as it passes close to Mars. The ESA had announced weeks earlier, their statement carrying the measured tone of institutional confidence. But beneath that sterile language lies something far more extraordinary. These aren't just routine observations of a distant object. These are humanity's first close-range encounters with a visitor from another star system. The mathematics of this moment are staggering. 3I Atlas approaches within 30 million kilometers of Mars on October 3rd, a distance that sounds vast until you realize it represents the closest any human-made instrument has ever come to an interstellar object. While Earth-based telescopes strain to glimpse this cosmic wanderer across hundreds of millions of kilometers, Mars-based cameras can resolve details that terrestrial astronomy can only dream of achieving. But here's what makes the silence so unsettling. The ESA's statement, clinical in its precision, reveals something troubling about the flow of information. They announce their intention to observe, they specify their time frame, they even provide the exact distance of closest approach. What they don't mention is when these potentially revolutionary images will be shared with the world that funded their creation. Mars Express has been humanity's eye in Martian orbit since 2003, its high-resolution stereo camera capable of distinguishing features mere meters across on the planet's surface. When that same technological precision is directed toward an interstellar visitor, the potential for discovery becomes almost overwhelming. Every pixel captured could contain information about stellar formation processes in alien solar systems, about the chemical composition of worlds we will never visit, about the fundamental building blocks of cosmic evolution itself. The ExoMars Trace Gas Orbiter brings even more sophisticated capabilities to bear on this unprecedented observation. Its spectrometers can analyze the chemical fingerprints of materials across vast distances, potentially revealing the atomic secrets that 3I Atlas carries from its journey through interstellar space. This isn't just photography, it's cosmic archaeology, the systematic excavation of secrets buried in ice and rock from beyond our solar neighborhood. Yet, as October 3rd passes into October 4th, then October 5th, the promised flood of revelatory imagery fails to materialize. The ESA's website updates with routine mission status reports, standard operational data, the mundane housekeeping of space exploration. But the images that could reshape our understanding of interstellar visitors remain locked behind institutional protocols and bureaucratic procedures. This creates a fascinating paradox in the modern age of space exploration. Never before have we possessed such sophisticated tools for cosmic observation, yet never before has the gap between capability and disclosure felt so deliberately maintained. The technology exists to provide real-time views of humanity's first close encounter with an interstellar object, but the institutional framework ensures that such revelations unfold according to careful schedules rather than natural curiosity. The mechanical watchers above Mars continue their silent vigil, their data streams flowing back to Earth through the Deep Space Network's massive radio dishes. Somewhere in mission control centers across Europe, teams of scientists pore over incoming telemetry, processing images that may contain the most significant astronomical discoveries of the decade. But between those control rooms and public awareness lies a carefully constructed barrier of review processes, analysis protocols, and administrative approvals. What makes this particularly intriguing is the contrast with previous ESA missions. When Mars Express captured stunning images of Martian landscapes or atmospheric phenomena, those pictures often appeared online within days of acquisition. When ExoMars detected seasonal variations in atmospheric methane, the agency rushed to share those findings with the global scientific community. But 3I Atlas observations seem subject to different rules, different timelines, different levels of scrutiny. The silence from these mechanical watchers becomes more meaningful when you consider what they might actually be seeing. 3I Atlas isn't just another chunk of space rock following predictable orbital mechanics. It's an object that has demonstrated unusual properties throughout its journey through our solar system, properties that have puzzled astronomers and challenged existing models of cometary behavior. As these sophisticated European instruments focus their attention on humanity's first interstellar visitor, they're potentially witnessing phenomena that no Earth-based telescope could ever hope to observe. They might be documenting the interaction between interstellar materials and our sun's solar wind, capturing the spectroscopic signatures of elements forged in alien stellar furnaces, recording the precise mechanics of how objects from other star systems behave when they encounter our cosmic neighborhood. But that potential revelation remains locked behind institutional walls. subject to review processes and approval hierarchies that seem designed more for control than for discovery. The mechanical watchers above Mars have seen something extraordinary, but their human operators have chosen silence over immediate sharing, procedure over passion, institutional caution over cosmic wonder. The question that haunts October 3rd and the days that follow isn't whether these sophisticated instruments successfully observed 3I Atlas. The question is what they observed, and why that information seems to require such careful management before reaching the eyes of a world hungry for answers about our first close encounter with a visitor from the stars. While European satellites maintain their silent vigil above Mars, an even more troubling pattern emerges from across the Atlantic. NASA, the organization that has given humanity some of its most iconic images of cosmic discovery, finds itself wrapped in an information blackout that seems almost too convenient to be coincidental. The high-rise camera aboard NASA's Mars Reconnaissance Orbiter represents one of the most powerful optical instruments ever deployed in space. This technological marvel can resolve objects as small as individual boulders on the Martian surface from an orbital altitude of 300 kilometers. When directed toward 3I Atlas during its closest approach to Mars, HiRISE should theoretically capture images of unprecedented clarity and scientific value. But here's where the story takes a disturbing turn. The US government shutdown, timed with almost surgical precision to coincide with 3I Atlas's closest approach to Mars, creates what NASA officials describe as an information delivery problem. Their official website will not be updated during the shutdown. They announce with bureaucratic efficiency, new images, no matter how revolutionary, will remain locked behind administrative protocols until political theater resolves itself in Washington. The timing feels deliberate, calculated, suspicious. For months, astronomers have known that October 3rd would mark humanity's best opportunity to observe an interstellar visitor up close. Mission planners have had abundant time to prepare data release protocols, to establish automated systems for image distribution, to ensure that this once-in-a-generation scientific opportunity wouldn't be hampered by terrestrial political dysfunction. Yet as 3I Atlas makes its historic passage past Mars, NASA's most sophisticated imaging systems fall silent, not due to technical failure or mechanical breakdown, but because of administrative convenience. The most advanced space agency in human history, equipped with nuclear-powered rovers and instruments worth billions of dollars, claims inability to share basic imagery due to website maintenance protocols. This creates a fascinating study in institutional priorities. NASA can maintain real-time communication with spacecraft hundreds of millions of kilometers away, can execute complex orbital maneuvers with split-second precision, can coordinate simultaneous observations across multiple platforms orbiting different worlds. But they cannot apparently overcome the administrative challenge of sharing images during a government shutdown. The technical capabilities that remain operational during this supposed blackout reveal the selective nature of the information embargo. Raw imagery from the Perseverance rover continues flowing onto NASA's multimedia pages with mechanical regularity. The latest photos from October 3rd appear exactly on schedule, captured by the rover's right Mars-Cam-Z camera, as it continues its systematic exploration of Jezero crater. This selective functionality raises uncomfortable questions about what can be shared and what cannot, about which data streams are considered essential and which are deemed discretionary. The same technical infrastructure that delivers routine geological imagery from the Martian surface apparently cannot handle the administrative complexity of sharing unprecedented observations of humanity's first interstellar visitor. The HiRISE camera continues its programmed observations regardless of terrestrial political complications. Its mechanical precision operates independently of government shutdowns, budget negotiations, or administrative convenience. The images are being captured, the data is being transmitted, the historic observations are occurring exactly as planned. But between those images and public awareness lies a bureaucratic barrier that seems designed more for control than for technical necessity. What makes this particularly troubling is NASA's historical approach to major discoveries. When the agency captured the first images of water flowing on Mars, those pictures circulated globally within hours. When their rovers detected organic compounds in Martian soil, press releases and technical briefings followed immediately. When Hubble telescope revealed distant galaxies in unprecedented detail, the agency rushed to share those cosmic visions with a world hungry for wonder. But 3I Atlas's observations seem subject to different rules, different timelines, different levels of scrutiny. The same organization that built its reputation on dramatic reveal moments and carefully choreographed press conferences suddenly finds itself constrained by administrative protocols that conveniently coincide with humanity's first close-range encounter with an interstellar object. The digital blackout extends beyond simple image sharing into broader patterns of communication about the 3i observations. NASA's social media channels, typically alive with real-time updates about ongoing missions, fall strangely quiet about activities related to the interstellar visitor. Mission status updates continue for routine operations, but references to the historic observation opportunity disappear behind veils of administrative procedure. This silence becomes more meaningful when contrasted with the agency's typical approach to public engagement. NASA has mastered the art of building public excitement around space exploration, of transforming technical achievements into shared moments of human wonder. Their ability to communicate complex scientific concepts through compelling imagery and accessible language has inspired generations of students, scientists, and space enthusiasts. Yet during humanity's first opportunity to observe an interstellar visitor up close, that same communication machinery falls conspicuously silent. The organization that turned rover landings into global events, that made telescope imagery into popular art, that transformed space exploration into shared human experience, suddenly finds itself unable to share what may be the most significant astronomical observations of our lifetime. The technical capabilities remain fully operational. The political justifications seem conveniently timed. The historical precedents suggest a very different approach to major discoveries, and the implications of what might be contained in those carefully withheld images grow more intriguing with each day of continued silence. On the surface of Mars, far below the orbital dance of sophisticated surveillance satellites, a six-wheeled robot continues its methodical exploration of Jezero crater, seemingly oblivious to the cosmic drama unfolding overhead. NASA's Perseverance rover, designed to search for ancient signs of microbial life in Martian rocks, finds itself positioned as humanity's most unlikely witness to an interstellar encounter. The rover's daily routine continues with mechanical precision, even as government shutdowns and institutional silence swirl around the agencies that control it. Every Martian day, Perseverance awakens to a programmed schedule of geological analysis, sample collection, and systematic photography. Its right Mastcam Z camera captures hundreds of images, documenting everything from microscopic rock textures to sweeping panoramic vistas of the ancient crater that serves as its scientific playground. But on October 1st, something extraordinary may have entered those routine observations. Raw imagery flows from Perseverance with bureaucratic regularity, appearing on NASA's multimedia pages, regardless of political complications back on Earth. These images represent the most unfiltered view of Mars that humanity possesses, direct digital captures from the planet's surface, transmitted across interplanetary space without editorial intervention or institutional review. They show exactly what the rover's cameras see, exactly when they see it, without the careful curation that typically accompanies major space discoveries. This creates a fascinating paradox in the carefully managed flow of information about 3i. While orbital platforms operated by both NASA and ESA maintain careful silence about their observations, a robot designed for geological research continues broadcasting its unedited visual experiences to anyone willing to examine the raw data streams. The irony deepens when you consider Perseverance's original mission parameters. This rover was never intended to observe interstellar visitors or participate in astronomical surveys. Its sophisticated camera systems were designed to analyze rock formations, identify potential biosignatures, and document the geological history of a world that died billions of years ago. Yet through cosmic coincidence and orbital mechanics, it finds itself positioned as perhaps the only source of unfiltered observations during humanity's first close encounter with a visitor from another star system. The rover's perspective offers something that no orbital platform can provide: a ground-level view of how an interstellar object appears from a planetary surface other than Earth. While sophisticated space-based telescopes strain to resolve distant details, Perseverance sits beneath the thin Martian atmosphere, its cameras pointing upward toward a sky that holds secrets no human eye has ever witnessed directly. The mechanical routine of the rover's observations becomes almost poetic when viewed against the backdrop of cosmic significance. Every few hours, Perseverance turns its cameras skyward, capturing systematic images of the Martian heavens as part of its atmospheric monitoring protocols. These routine observations, designed to track weather patterns and atmospheric conditions, inadvertently create a time-lapse record of anything unusual that might cross the robot's field of view. On October 1st, those routine atmospheric observations may have captured something unprecedented. Hidden within the systematic documentation of Martian weather patterns and atmospheric conditions, buried among hundreds of routine geological images, a faint smudge of light appears in exactly the location where orbital calculations predict 3I at Luz should be visible from the planet's surface. This presents a remarkable contrast to the institutional silence surrounding official 3I at Luz observations. While government agencies claim administrative inability to share carefully planned images of the interstellar visitor, a robot conducting routine geological research accidentally documents the same cosmic event through its regular operational procedures. The most significant astronomical observation of the decade may have been captured not by sophisticated space telescopes specifically trained on the target, but by a geology rover going about its normal business. The continuing flow of raw imagery from Perseverance creates an unprecedented opportunity for independent analysis of potentially historic observations. Unlike the carefully processed and institutionally reviewed images that typically emerge from major space discoveries, these raw captures are available to anyone with the technical knowledge to analyze them. Amateur astronomers, citizen scientists, and independent researchers can examine the same data streams that professional astronomers use, applying their own analytical techniques to search for evidence of humanity's first close encounter with an interstellar visitor. This democratization of space data represents a fundamental shift in how astronomical discoveries unfold in the modern era. Previously, major cosmic revelations emerged through carefully orchestrated announcements from official institutions, filtered through layers of review and interpretation before reaching public awareness. But the continuous flow of raw data from robotic explorers creates opportunities for discoveries to emerge through independent analysis, citizen science, and grassroots investigation. The rover's position within Jezero crater provides unique advantages for observing objects in the Martian sky. The crater's elevated rim creates a natural observatory environment, shielding the rover's cameras from certain sources of atmospheric interference, while providing clear sightlines towards specific regions of space. The thin Martian atmosphere offers less optical distortion than Earth's dense atmospheric layers, potentially allowing surface-based observations that rival the clarity of space-based telescopes. But perhaps most significantly, Perseverance operates according to pre-programmed schedules that remain independent of terrestrial political complications. While government shutdowns and institutional protocols may delay the release of carefully planned observations, the rover continues its systematic documentation of everything within its field of view. Its mechanical objectivity ensures that historic cosmic events are recorded regardless of human intentions, institutional priorities, or administrative convenience. The question that emerges from this accidental witness is whether the most significant astronomical discovery of our time will first be revealed, not through official channels and carefully prepared announcements, but through the patient analysis of routine geological imagery captured by a robot that never intended to make history. In a small studio somewhere on Earth, far from the gleaming mission control centers of space agencies and the sophisticated radar dishes of deep space networks, an astrophotographer named Simeon Schmalz hunches over his computer screen, methodically examining images that most people would dismiss as meaningless static. His tools are humble compared to billion-dollar spacecraft: basic image processing software, consumer-grade hardware, and an abundance of patience that institutional science rarely possesses. But tonight, that patience is about to pay off in ways that challenge the entire framework of how astronomical discoveries unfold in the modern era. Schmalz represents something that makes space agencies deeply uncomfortable: an independent analyst with the technical skills to examine the same data streams they use, the persistence to look where they might prefer he didn't, and the freedom to share his discoveries without layers of institutional approval. While official observers maintain careful silence about their 3I at Luz observations, this amateur detective applies the fundamental tools of astronomical investigation to publicly available raw imagery. 20 images from NASA's Perseverance rover, captured on October 1st as the rover conducted routine atmospheric monitoring, sit open across multiple windows on Schmalz's computer screen. To casual observers, these images show nothing more than the routine documentation of Martian skies, the same atmospheric monitoring that the rover conducts every few days as part of its standard operational protocols. But Schmalz sees something different. His trained eye recognizes that these routine images were captured at exactly the right time, from exactly the right location, pointing in exactly the right direction to potentially document something unprecedented. The mechanical objectivity of robotic observation has created an opportunity that careful institutional planning might never have achieved. The process he employs is called image stacking, a technique that combines multiple photographs of the same celestial region to reveal details too faint to appear in individual frames. By carefully aligning 20 separate images and mathematically averaging their pixel values, Schmaus can effectively increase the sensitivity of his analysis beyond what any single observation could achieve. It's digital archaeology, excavating signal from noise through patient mathematical manipulation. Hour after hour, he works through the technical challenges of processing images never intended for astronomical analysis. The rover's cameras were calibrated for geological observation, not astronomical photography. Their exposure settings, color balance and focus parameters were optimized for examining rocks and soil samples, not for detecting faint objects against the Martian sky. Converting this geological imagery into astronomical data requires technical expertise that few people possess and institutional determination that even fewer maintain. But as the processed images begin to emerge from his stacking analysis, something extraordinary appears on Schmaus's screen, in the constellation Corona Borealis, precisely where orbital calculations predict 3I Atlas should appear from Mars's surface. A faint smudge of light materializes in the processed imagery. It's almost invisible, the kind of detection that requires multiple confirmation procedures and careful verification against instrumental artifacts. But it's there, consistent across multiple frames, positioned exactly where an interstellar visitor should appear during its closest approach to the red planet. I think Perseverance may have spotted interstellar comet 3I Atlas last night from Mars, Schmaus announces on Blue Sky, his excitement barely contained within the constraints of social media messaging. The simple statement carries implications that ripple far beyond its casual tone. If confirmed, this represents the first public documentation of 3I Atlas, as seen from another planetary surface, achieved not through institutional programs worth billions of dollars, but through individual curiosity and amateur determination. The discovery process reveals fundamental tensions in modern space exploration between institutional control and democratic access to information. While government agencies possess the most sophisticated equipment and the largest budgets, they also operate within bureaucratic frameworks that can delay or complicate the revelation of important discoveries. Amateur investigators like Schmaus operate with fewer resources but greater freedom, able to pursue interesting leads without institutional approval or administrative oversight. His technical analysis continues beyond the initial detection. Using astronomical software, Schmaus compares the position of his faint smudge against predicted orbital parameters for 3I Atlas. The match is remarkably precise, close enough to suggest that his detection represents genuine observation rather than instrumental artifact or processing error. The new orbit parameters in Stellarium are a pretty good match, he notes with the understated precision of someone who understands the significance of what he's discovered. This represents something unprecedented in the history of space exploration. An amateur astronomer, using publicly available robotic imagery to potentially achieve the first confirmed surface-based observation of an interstellar object from another planet. The democratization of space data, combined with increasingly sophisticated amateur analysis tools, has created opportunities for discoveries that bypass traditional institutional gatekeepers entirely. The emotional weight of the moment extends beyond simple technical achievement. Schmaus has spent hours examining imagery that space agencies apparently consider too routine to warrant immediate analysis. His discovery emerges not from carefully planned observation campaigns or multi-million-dollar instruments, but from the patient application of basic astronomical techniques to data that was freely available to anyone willing to look. This creates a fascinating inversion of traditional scientific hierarchy. While professionally trained astronomers operating billion-dollar spacecraft maintain careful silence about their 3I Atlas observations, an amateur investigator working with consumer-grade tools potentially achieves the first public confirmation of the interstellar visitor's presence in Martian skies. The broader implications of Schmaus's discovery extend far beyond the specific detection of one faint smudge in processed imagery. His work demonstrates that the era of controlled revelation in space exploration may be ending, replaced by a more democratic model where significant discoveries can emerge from independent analysis of publicly available data. The same technological advances that enable sophisticated robotic exploration also enable amateur investigators to participate in the discovery process at levels previously reserved for institutional science. As word of his detection spreads through social media and amateur astronomy communities, Schmorse finds himself at the center of something larger than a simple astronomical observation. He has become the human face of curiosity triumphant over institutional caution. The individual whose persistence revealed secrets that organizations worth billions of dollars seemed reluctant to share immediately. The faint smudge in his processed images may represent humanity's first surface-based view of an interstellar visitor from another world, achieved not through careful institutional planning but through the timeless combination of curiosity, patience, and refusal to accept that some secrets should remain hidden. In the processed images on Simeon Schmosse's computer screen, the detection looks almost anticlimactic, a barely perceptible brightening against the background noise of Martian atmospheric photography, so faint that it requires multiple verification steps to distinguish from instrumental artifacts. But this unremarkable smudge of pixels represents something profound enough to challenge our understanding of how astronomical discoveries unfold in the modern era. The technical details of the detection tell a story that extends far beyond simple astrophotography. When 20 separate images captured by NASA's Perseverance rover are mathematically combined through digital stacking techniques, they reveal signal buried beneath the noise threshold of individual observations. This faint enhancement appears in exactly the position where orbital mechanics predict 3I at Lus should be visible from Mars's surface during its October 1st passage through Martian skies. But the significance extends far beyond the simple fact of detection. The precise positional match between Schmorse's smudge and predicted coordinates for 3I at Lus represents a kind of cosmic validation that occurs rarely in amateur astronomy. When you're dealing with objects so distant and faint that they exist at the very edge of observational capability, false positives become a constant concern. Instrumental noise, processing artifacts, and random pixel fluctuations can create apparent detections that disappear under careful scrutiny. Yet Schmorse's finding survives multiple levels of verification. The enhancement appears consistently across different processing approaches. Its position matches orbital predictions with remarkable precision. Its brightness characteristics align with theoretical expectations for how 3I at Lus should appear from Mars's surface at that specific time and location. Each independent confirmation reduces the probability that this detection represents anything other than genuine observation of humanity's first interstellar visitor. The location within Corona Borealis adds another layer of significance to the discovery. This constellation, visible from Mars during the rover's October 1st observations, provides a stellar reference frame that allows precise position measurements. When Schmoss compares his detection coordinates against star charts and orbital predictions, the match becomes even more compelling. The interstellar visitor appears exactly where mathematics says it should, captured by cameras never intended for such observations, detected through analysis techniques that space agencies seem reluctant to apply immediately to their own data. This positional precision reveals something profound about the nature of 3I at Lus itself. The object's trajectory through our solar system follows gravitational laws with mathematical exactness, allowing astronomers to predict its position with stunning accuracy across vast distances and extended time periods. When amateur analysis of robotic imagery confirms those predictions to within fractions of degrees, it validates both our understanding of celestial mechanics and the reality of what's being observed. The faintness of the detection offers clues about 3I at Lus's physical characteristics during its passage past Mars. Interstellar objects carry limited ability to reflect sunlight compared to native solar system bodies, and their composition may differ significantly from familiar comets and asteroids. The barely perceptible brightness recorded in Perseverance's imagery suggests an object that has traveled immense distances while maintaining structural integrity, carrying within its frozen nucleus the chemical signatures of stellar processes from beyond our Sun. But perhaps most significantly, the successful detection demonstrates the power of persistence in astronomical investigation. While institutional observers maintain careful silence about their observations, patient amateur analysis reveals that the data necessary for major discoveries already exists within publicly available information streams. The same robotic imagery that documents routine geological formations on Mars also captures unprecedented views of interstellar visitors, waiting only for someone with sufficient curiosity and technical skill to extract the buried signals from background noise. The mathematical elegance of the confirmation process reveals how modern amateur astronomy has evolved beyond simple stargazing into sophisticated scientific investigation. Schmauzer's analysis employs the same fundamental techniques used by professional observatories: image stacking, position measurement, statistical verification, and comparison against theoretical predictions. The tools of astronomical discovery have become sufficiently democratized that individual investigators can achieve results that previously required institutional resources and professional training. This democratization carries profound implications for how space exploration discoveries unfold in the coming decades. As robotic missions generate increasingly vast streams of publicly available data, opportunities multiply for independent investigators to make significant findings through patient analysis of information that official sources may not immediately examine or release. The traditional model of carefully controlled revelation through institutional channels begins to give way to a more open process where discoveries can emerge from multiple sources simultaneously. The detection also highlights the unique advantages of Mars-based observation for studying interstellar visitors. The red planet's position during 3I Atlas's closest approach provides viewing angles and proximity impossible to achieve from Earth-based telescopes. The thin Martian atmosphere creates fewer optical distortions than Earth's dense atmospheric layers. The mechanical objectivity of robotic observation eliminates human bias and maintains consistent data collection, regardless of terrestrial political complications. When Schmauzer's processed images reveal that faint enhancement in Corona Borealis, they demonstrate that some of the most significant astronomical observations of our time may be hidden within routine data streams, waiting for independent analysis to reveal their importance. The interstellar visitor's passage past Mars was captured not only by sophisticated orbital platforms operating under institutional control, but also by geological rovers conducting routine atmospheric monitoring, their mechanical objectivity documenting cosmic history as it unfolded overhead. The faint smudge in those stacked images represents more than just successful detection of an interstellar object. It represents the moment when amateur determination overcame institutional caution, when individual curiosity revealed secrets that billion-dollar spacecraft seemed reluctant to share immediately, and when the democratic nature of modern space exploration asserted itself against the careful control of traditional astronomical discovery. In that barely perceptible brightening against the Martian sky lies proof that the universe refuses to cooperate with human attempts to manage the timing of revelation. The cosmos operates according to its own schedule, creating opportunities for discovery that persist regardless of administrative convenience or institutional priorities. And sometimes it takes an amateur detective with patience and processing software to reveal what professional observers already know but haven't yet chosen to share. As official space agencies maintain their careful silence about 3I Atlas observations, an entirely different information ecosystem springs to life across social media platforms, amateur astronomy forums, and citizen science networks. This underground railway of cosmic discovery operates according to different rules than institutional science, rules based on immediate sharing, collaborative analysis, and transparent investigation, rather than careful review and managed revelation. The pattern emerges gradually at first, then accelerates into something resembling a digital gold rush. Amateur astronomers around the world begin sharing images that reportedly show 3I Atlas captured through various telescopes and analysis techniques. Some of these detections appear legitimate, carefully processed photographs showing faint enhancements at predicted coordinates. Others look more questionable, indistinct smudges that could represent anything from genuine astronomical observations to instrumental artifacts or wishful thinking. But within this chaotic flood of competing claims and unverified observations, something remarkable begins to emerge. The collaborative nature of amateur astronomy creates natural quality control mechanisms that institutional science often lacks. When someone shares a potential detection of 3I Atlas on social media, the image immediately faces scrutiny from dozens of independent analysts, equipped with their own processing software, comparison databases, and technical expertise. False positives get identified and dismissed quickly. Genuine observations receive confirmation and enhancement from multiple independent sources. This distributed verification process operates at speeds that traditional academic peer review could never match. Within hours of Schmaus posting his Perseverance analysis on Blue Sky, amateur astronomers across multiple continents are downloading the same raw imagery, applying their own processing techniques, and either confirming or challenging his detection. The social media ecosystem becomes a real-time observatory where discoveries are tested, refined, and validated through immediate collaborative investigation. The contrast with official channels becomes increasingly stark as days pass without institutional image releases. While government agencies claim administrative difficulties preventing timely sharing of their 3i Atlas observations, amateur networks demonstrate that significant astronomical analysis can occur within hours of data availability. The same information streams that support patient institutional review also enable rapid independent investigation by communities motivated more by curiosity than by bureaucratic procedure. Platform after platform fills with increasingly sophisticated amateur analyses of the interstellar visitor. Twitter threads break down the orbital mechanics of 3i Atlas's trajectory past Mars. Reddit communities collaborate on processing techniques for extracting faint signals from noisy robotic imagery. Discord servers become real-time coordination centers, where amateur astronomers share processing methods, compare results, and plan coordinated observation strategies. This social media astronomy renaissance reveals capabilities that traditional institutions seem reluctant to acknowledge. Amateur investigators equipped with consumer-grade hardware and open-source software can achieve analytical results that rival professional observatories in certain circumstances. The combination of publicly available robotic data, sophisticated processing algorithms, and distributed human intelligence creates opportunities for discovery that operate independently of institutional gatekeepers. Yet within this democratic explosion of astronomical investigation, patterns of caution and verification emerge that demonstrate the maturity of amateur science communities. Experienced contributors quickly learn to distinguish between legitimate detections and hopeful artifacts. Claims require supporting evidence, processing methods must be transparent and reproducible, and extraordinary assertions demand extraordinary verification through multiple independent confirmations. The quality gradient among social media observations tells its own story about the current state of 3i Atlas detection capabilities. The clearest and most convincing images emerge from amateur astronomers with significant technical expertise and sophisticated processing equipment. These investigators understand the challenges of detecting extremely faint objects, the importance of statistical verification, and the need for careful position measurement against stellar reference frames. Less convincing observations come from enthusiastic but less technically sophisticated contributors who may be detecting instrumental noise, processing artifacts, or atmospheric phenomena rather than genuine astronomical objects. But even these questionable contributions serve a valuable function in the amateur astronomy ecosystem. They provide opportunities for more experienced investigators to demonstrate proper analysis techniques and help educate newer contributors about the challenges of extreme astrophotography. The educational aspect of this social media astronomy explosion extends far beyond simple image sharing. Detailed explanations of processing techniques spread rapidly through amateur communities, enabling more people to participate meaningfully in the analysis process. Experienced astrophotographers share tutorials on image stacking, noise reduction, and position measurement. Software developers contribute tools specifically designed for analyzing robotic imagery from Mars missions. This knowledge transfer creates a positive feedback loop that increases the overall analytical capability of amateur astronomy communities. As more people learn sophisticated processing techniques, the number of independent investigators capable of meaningful 3i Atlas analysis grows rapidly. The distributed intelligence of social media networks applies increasingly sophisticated tools to the challenge of detecting and characterizing humanity's first close encounter with an interstellar visitor. The geographic distribution of amateur contributors adds another dimension to the social media investigation ecosystem. Observers from different time zones, different hemispheres, and different cultural backgrounds bring diverse perspectives to the analysis process. Techniques developed by amateur astronomers in one region get adopted and refined by investigators elsewhere, creating a truly global collaborative effort that transcends the institutional boundaries of traditional space science. Perhaps most significantly, the social media underground demonstrates that the era of controlled scientific revelation may be ending. When data streams from robotic explorers become publicly available in near real time, opportunities for major discoveries exist independently of institutional priorities and administrative procedures. The same technological infrastructure that enables sophisticated space missions also enables amateur investigators to participate directly in the discovery process. The question that emerges from this social media explosion isn't whether amateur astronomers can detect 3I at LUS independently of official channels. Schmaus and others have already demonstrated that capability. The question is whether this represents a fundamental shift toward more democratic space exploration, where significant discoveries emerge through collaborative investigation rather than institutional revelation, and where the timing of cosmic discovery is determined more by natural curiosity than by administrative convenience. The technical advantages of Mars-based observation create opportunities for studying 3I at LUS that no Earth-based telescope could ever hope to achieve, yet the full significance of this unprecedented viewing opportunity remains shrouded behind institutional protocols and administrative convenience. Understanding what makes Martian observation so revolutionary requires examining both the physics of interplanetary astronomy and the politics of information control that shape how discoveries are revealed to the world. Mars orbits the Sun at an average distance of 228 million kilometers, compared to Earth's 150 million kilometers. During 3I at LUS's October approach, this seemingly modest difference in orbital position creates viewing opportunities that transform the entire observational equation. While Earth-based telescopes struggle to resolve details across hundreds of millions of kilometers of intervening space, Mars-based instruments achieve proximity that reduces observational challenges by orders of magnitude. The geometric advantages extend beyond simple distance reduction. Mars's orbital position during the 3I at LUS encounter provides viewing angles that reveal aspects of the interstellar visitor completely invisible from Earth's perspective. The same object that appears as a barely detectable point of light through terrestrial telescopes becomes a resolved target for Martian cameras, potentially revealing surface features, structural details, and activity patterns that could revolutionize our understanding of how interstellar objects behave when they encounter alien solar systems. But perhaps most significantly, Mars-based observation occurs without the atmospheric distortions that plague even the most sophisticated Earth-based astronomy. The red planet's thin atmosphere, less than 1% the density of Earth's atmospheric layers, creates observational conditions that approach the clarity of space-based telescopes while maintaining the stability and extended observation periods possible only from planetary surfaces. This creates a unique hybrid observational environment. Cameras positioned on a planetary surface but operating in conditions closer to space-based astronomy than terrestrial observation. The combination allows for extended observation periods, precise tracking of target motion, and systematic documentation of changes in the object's appearance over time. Unlike brief flyby missions or limited telescope viewing windows, Mars-based observation of 3I at LUS can continue for days or weeks, building comprehensive databases of information about humanity's first close encounter with an interstellar visitor. The instrumental capabilities deployed for Mars observation represent the cutting edge of robotic astronomy. The high-rise camera aboard NASA's Mars Reconnaissance Orbiter can distinguish features smaller than individual boulders on planetary surfaces. When directed toward an interstellar object at close range, this level of resolution could potentially reveal details about 3I at LUS's structure, composition, and activity that no previous observation has achieved. Similarly, the spectrometric instruments aboard various Mars missions offer opportunities for chemical analysis of interstellar materials that would be impossible from Earth-based platforms. These instruments can analyze the spectral signatures of gases and particles released as 3I at LUS interacts with solar radiation, potentially revealing the atomic composition of materials that originated in alien stellar systems billions of years ago. The coordination required for optimal Mars-based observation of 3I at LUS demonstrates the sophisticated planning capabilities of modern space missions. Multiple spacecraft positioned at different orbital positions around Mars can provide simultaneous observations from varying angles, creating three-dimensional analysis opportunities that single-platform observation cannot achieve. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter, combined with NASA's Mars Reconnaissance Orbiter and various surface-based assets, represent an observational network more sophisticated than anything previously deployed for studying interstellar visitors. Yet this unprecedented observational capability remains largely invisible to public awareness due to institutional decisions about information timing and release protocols. The technical infrastructure exists to provide real-time sharing of potentially revolutionary observations, but administrative frameworks ensure that such sharing occurs according to careful schedules rather than natural discovery timelines. The data quality achievable through Mars-based observation of 3I at LUS likely exceeds anything possible from Earth-based analysis by factors of 10 or more. Resolution, signal-to-noise ratios, spectral analysis capabilities, and extended observation periods all favor the Martian platform significantly. This means that the most detailed and scientifically valuable information about humanity's first close encounter with an interstellar visitor is being collected by instruments positioned on and around the red planet. But the revolutionary potential of this data remains locked behind institutional review processes that seem designed more for control than for timely scientific revelation. While Mars-based instruments collect unprecedented information about interstellar object composition, structure, and behavior, the timing of that information's release to the scientific community and general public depends more on administrative priorities than on the natural pace of cosmic discovery. The contrast between capability and accessibility becomes particularly stark when considering the historical significance of these observations. 3I at LUS represents humanity's first opportunity to study an interstellar visitor at close range using sophisticated modern instruments. The data being collected during its passage past Mars will likely influence astronomical research for decades to come, providing baseline information about interstellar object characteristics that will guide future observation strategies and theoretical models. Yet this historically significant data remains subject to the same administrative procedures and review protocols that govern routine mission operations. The unprecedented nature of the observations doesn't seem to have triggered corresponding changes in information sharing procedures or recognition that standard protocols may be inadequate for managing discoveries of such profound significance. The technical achievements of Mars-based 3I at LUS observation represent a triumph of human engineering and scientific planning. The successful coordination of multiple sophisticated platforms to observe an interstellar visitor demonstrates capabilities that previous generations of astronomers could only dream of achieving. But the administrative management of those achievements reflects institutional priorities that seem more concerned with control than with the timely sharing of potentially revolutionary discoveries. Behind the Martian veil, unprecedented observations of humanity's first interstellar visitor continue according to mechanical schedules, independent of terrestrial political complications. The question isn't whether extraordinary data is being collected. The technical capabilities ensure that it is. The question is when that data will be shared with a world hungry for answers about our first close encounter with a visitor from the stars. As October fades into cosmic history, and 3I at LUS begins its journey back toward the outer reaches of our solar system, European mission planners prepare for what may prove to be the most scientifically valuable observation period of the entire interstellar encounter. The Jupiter Icy Moons Explorer, known as JUICE, drifts through its carefully calculated trajectory toward the outer solar system. But between November 2nd and 25th, its sophisticated instruments will turn their attention to humanity's departing interstellar visitor. The timing of these November observations carries profound scientific significance that extends far beyond simple astronomical photography. 3I at LUS will have completed its closest approach to the Sun by early November, experiencing the maximum heating and activity that our star can impose on materials that originated in another stellar system. This post-perihelion observation period offers opportunities to study interstellar object behavior under conditions that no previous mission has ever achieved. As JUICE looks towards 3I at LUS, so soon after its closest approach to the Sun, it is likely to have the best view of the comet in a very active state. The European Space Agency explains with characteristic technical understatement. But this clinical description barely captures the revolutionary nature of what may be documented during those 3 weeks in November. The physical processes that occur when interstellar materials encounter the intense radiation environment near our Sun create phenomena that terrestrial laboratories cannot reproduce and theoretical models can only approximate. Ice sublimation, gas release, particle acceleration, and electromagnetic interactions between alien materials and solar radiation produce observable effects that reveal fundamental information about the chemical composition and structural characteristics of objects that have traveled between the stars. JUICE's instrumental suite brings capabilities to this observation opportunity that surpass anything previously deployed for studying interstellar visitors. Advanced spectrometers can analyze the chemical fingerprints of gases released as 3I at LUS responds to solar heating, High-resolution cameras can document the formation and evolution of the characteristic halo and tail that distinguish active comets from dormant space debris. Particle detectors can analyze the composition of materials ejected from the object's nucleus as volatile compounds vaporize under solar influence. But the November window represents more than just superior instrumental capabilities. It offers timing that may never be replicated in human history. The combination of an interstellar visitor at peak activity levels, sophisticated analysis instruments positioned for optimal observation, and the accumulated experience from months of three-eye-at-loss study creates conditions ideal for breakthrough discoveries about the nature of objects that originate beyond our solar neighborhood. The anticipated appearance of three-eye-at-loss during its post-perihelion active phase promises visual documentation that could transform public understanding of interstellar visitors. Instead of the barely detectable smudges and faint enhancements that have characterized most observations to date, November should reveal a bright halo around its nucleus and a long tail stretching out behind it, according to ESA projections. This transformation from subtle detection challenge to dramatic visual spectacle reflects the fundamental physics of how cometary objects respond to solar radiation. The same heating processes that create barely detectable gas releases during distant approach phases can produce spectacular displays of activity when objects reach their closest solar distances. For three-eye-at-loss, this means that its most scientifically valuable and visually compelling characteristics will be documented during exactly the observation period when JUICE's instruments are focused on the target. The 3-week duration of the November observation window allows for systematic documentation of how interstellar object activity evolves over time. Rather than brief snapshots or limited viewing opportunities, JUICE can track changes in three-eye-at-loss's appearance, composition and behavior as it responds to varying levels of solar influence during its departure from the inner solar system. This extended observation period enables analysis of activity cycles, structural changes, and compositional variations that brief encounters could never reveal. The scientific implications of successful November observations extend far beyond the immediate study of three-eye-at-loss itself. This interstellar visitor represents our first close-range encounter with materials that originated in alien stellar systems, carrying within its frozen nucleus chemical signatures from stellar formation processes that occurred under conditions potentially very different from those in our own solar neighborhood. Understanding how these alien materials behave when they encounter our sun's radiation environment provides crucial calibration data for theoretical models of interstellar object composition and behavior. The information gathered during JUICE's November observations will influence how astronomers interpret future interstellar visitor encounters and guide the development of more sophisticated detection and analysis strategies for objects that may visit our solar system in the coming decades. Yet the promise of these revolutionary November observations remains subject to the same institutional review and release protocols that have characterized the entire three-eye-at-loss encounter. The European Space Agency's careful language about what might be observed during the November window provides little indication of when such observations might be shared with the scientific community or general public. This creates a fascinating tension between the acknowledged scientific importance of the November observation period and the institutional frameworks that control how discoveries are revealed. The same organization that recognizes these observations as potentially providing the best view of the comet in a very active state also maintains administrative procedures that could delay the sharing of such revolutionary imagery for weeks or months after acquisition. The November window represents humanity's last best opportunity to study three-eye-at-loss before it disappears back into the cosmic void between stars. The combination of peak activity levels, sophisticated instruments, and optimal viewing geometry creates conditions that may never be replicated for any future interstellar visitor. The data collected during those 3 weeks in November will likely represent the most comprehensive analysis of an interstellar object that human civilization achieves for decades to come. But between the collection of that potentially revolutionary data and its revelation to a world hungry for answers about our first interstellar visitor, lies the same careful institutional control that has characterized the entire three-eye-at-loss encounter. The promise of extraordinary discoveries remains balanced against administrative procedures that prioritize careful review over immediate sharing, institutional caution over public curiosity. As November approaches, the question isn't whether JUICE will successfully observe three-eye-at-loss during its most active and scientifically valuable phase. The technical capabilities and orbital mechanics ensure that it will. The question is whether the revolutionary discoveries made during those observations will be shared with the speed and transparency that such historically significant findings deserve. Beneath the administrative silence and institutional protocols surrounding 3I at Lus observations lies a deeper mystery that challenges our fundamental understanding of what interstellar visitors should look like, how they should behave, and what their presence in our solar system means for theories of cosmic evolution and planetary formation processes throughout the galaxy. The anomalous characteristics that have puzzled astronomers since 3I at Lus's initial detection in July reveal an object that defies easy categorization within existing frameworks of cometary science. Unlike the predictable behavior patterns exhibited by native solar system comets, this interstellar visitor displays properties that seem to shift and change in ways that theoretical models struggle to explain adequately. Traditional cometary objects follow well-understood patterns of activity as they approach the Sun. Ice sublimation creates predictable gas releases that form characteristic halos and tails. Structural changes occur according to established principles of thermal dynamics and gravitational stress. Brightness variations follow mathematical relationships based on distance from the Sun and the composition of volatile materials exposed to solar radiation. But 3I at Lus has demonstrated behavior that deviates from these established patterns in ways that suggest fundamental differences in composition, structure, or formation history compared to objects that originated within our solar system. These deviations provide tantalizing clues about the physical and chemical processes that occur in alien stellar systems, but they also create interpretive challenges that stretch existing theoretical frameworks to their limits. The spectroscopic signatures detected during early observations of 3I at Lus revealed chemical compositions that include familiar elements arranged in unfamiliar proportions. While the basic building blocks, water ice, carbon compounds, silicate minerals, match expectations for cometary objects, their relative abundances and structural arrangements suggest formation processes that occurred under conditions significantly different from those in our solar neighborhood. This compositional variance carries profound implications for understanding stellar system formation throughout the galaxy. If 3I at Lus originated in a stellar system with different metallicity, radiation environment, or planetary formation dynamics than our own, its chemical signatures provide direct observational evidence of how cosmic evolution proceeds under alternative conditions. The object becomes a traveling laboratory carrying experimental results from alien stellar chemistry across interstellar distances. The structural characteristics inferred from observational data add another layer of complexity to the composition mystery. 3I at Lus appears to maintain structural integrity despite the extreme temperature variations and gravitational stresses encountered during its journey through our solar system. This structural resilience suggests material properties or internal organization that differs significantly from typical solar system comets, which often fragment or disintegrate when subjected to similar environmental extremes. The activity patterns displayed by 3I at Lus during its approach to the Sun provide additional clues about its internal composition and structure. The timing, intensity, and spectral characteristics of gas releases reveal information about the distribution of volatile materials within the object's nucleus, the thermal conductivity of its structural materials, and the mechanical properties that govern how it responds to solar heating. But these activity patterns also raise fundamental questions about the formation environment that created such an object. The specific combination of volatile compounds, structural materials, and organizational characteristics observed in 3I at Lus suggests formation processes that may not occur in stellar systems similar to our own. Understanding what stellar conditions could produce such an object requires extending theoretical models beyond the relatively narrow range of environments represented by our solar system's formation history. The magnetic field interactions detected as 3I at Lus moves through the solar wind provide yet another dimension to the composition mystery. These electromagnetic signatures suggest the presence of metallic or electrically conductive materials within the object's structure, distributed in ways that create detectable magnetic responses to the charged particle environment of interplanetary space. Such magnetic properties have important implications for understanding how interstellar objects navigate the galactic magnetic field during their journeys between stellar systems. Objects with significant magnetic characteristics might follow trajectories influenced by galactic magnetic forces in addition to purely gravitational interactions. This could affect the probability of interstellar objects entering particular stellar systems and the likelihood of multiple visits from objects originating in the same distant stellar region. The density measurements derived from observational data reveal an object with mass distribution characteristics that don't match typical cometary compositions. 3I at Lus appears to be either more dense than expected for a loose agglomeration of ice and dust, or less dense than expected for a solid rocky body. This intermediate density suggests internal structure that combines materials in proportions or arrangements that differ from both typical comets and typical asteroids. Understanding the formation processes that could create objects with such intermediate characteristics requires considering stellar system environments with different evolutionary histories than our own. Perhaps 3I at Lus formed in a system where planetary formation proceeded differently, where different temperature and pressure conditions created alternative mineral structures, or where different chemical abundances led to novel material combinations. The thermal properties, inferred from 3I at Lus's response to solar heating, add another piece to the compositional puzzle. The object's brightness variations and activity patterns suggest thermal conductivity characteristics that don't match standard models of ice and rock mixtures. This could indicate the presence of materials with unusual thermal properties or structural arrangements that create novel heat transfer characteristics. These thermal anomalies have practical implications for understanding how interstellar objects might behave during future encounters with our solar system. If 3I at Lus represents a typical example of interstellar visitor composition, then standard models of cometary activity may require significant revision to account for the thermal properties of materials that formed under alien stellar conditions. The accumulating evidence from months of 3I at Lus observations paints a picture of an object that challenges existing categories of solar system bodies, while providing unprecedented insights into the diversity of materials and formation processes that occur throughout the galaxy. This interstellar visitor carries within its structure direct evidence of stellar chemistry and planetary formation dynamics that operated under conditions different from those that created our solar system. But fully understanding what 3I at Lus reveals about interstellar object composition requires access to the complete dataset of observations collected during its passage through our solar system. The most detailed spectroscopic analyses, the highest resolution structural imagery, and the most comprehensive activity monitoring remain locked behind institutional review processes that may take months to complete. The composition mystery of 3I at Lus represents more than just an interesting puzzle in astronomical cataloging. It offers our first direct observational evidence of how material formation and evolution proceed in stellar systems throughout the galaxy, providing crucial calibration data for theories of cosmic evolution and planetary formation that extend far beyond our immediate solar neighborhood. Patterns emerge from institutional behavior that reveal as much about the nature of 3I at Lus observations as any technical analysis of the object itself. The carefully orchestrated flow of information around humanity's first close encounter with an interstellar visitor follows protocols that seem designed more for managing public perception than for facilitating scientific discovery or satisfying natural human curiosity about cosmic phenomena. The timing of information releases, the selection of which data gets shared and which remains classified, the coordination between different space agencies, and the systematic delay between observation and revelation all point toward institutional frameworks that prioritize control over transparency, manage disclosure over immediate sharing of potentially revolutionary discoveries. This silence protocol becomes apparent when you examine the contrast between different types of space mission communications. Routine geological discoveries on Mars generate press releases within days of confirmation. Atmospheric measurements from various planetary missions appear in scientific journals within weeks of data collection. Even significant technical achievements or mission milestones receive immediate publicity through official channels and social media platforms. But 3I at Lus observations seem subject to different rules, different timelines, different levels of scrutiny before public release. The same institutional infrastructure that efficiently communicates routine space exploration achievements apparently requires extended review periods for sharing observations of humanity's first interstellar visitor at close range. The coordination between NASA and ESA regarding 3I at Lus information management suggests protocols that extend beyond individual agency decision-making. When both organizations simultaneously adopt similar approaches to information timing and release scheduling, it indicates planning and coordination that operates at levels above routine mission management. The silence isn't accidental or bureaucratic inefficiency, it's systematic and intentional. This coordinated approach to information control becomes particularly apparent when examining the technical capabilities that remain fully operational, despite claims of administrative limitations. The same infrastructure that allegedly cannot support timely sharing of 3I Atlas imagery continues to deliver routine mission updates, technical status reports, and administrative communications without apparent difficulty. The selective functionality reveals institutional priorities that place different values on different types of space exploration information. Routine mission operations continue with normal information sharing protocols, but observations of unprecedented significance require extended review periods and administrative procedures that may delay public awareness for weeks or months after data collection. The pattern extends beyond simple timing delays into more subtle forms of information management. When space agencies do release statements about 3I Atlas observations, those communications focus on technical capabilities and planned observation schedules rather than preliminary results or initial findings. The public receives information about what might be observed rather than what has been observed, about institutional intentions rather than scientific discoveries. This approach creates a fascinating inversion of traditional scientific communication, where preliminary results typically generate immediate excitement and detailed analysis, follows through extended research and peer review processes. The 3I Atlas observations seem subject to extended preliminary review before any public discussion of results occurs, reversing the normal sequence of discovery, sharing, and analysis that characterizes most astronomical research. The silence protocol also extends to scientific conferences and professional communications between researchers. While amateur astronomy communities buzz with analysis and speculation about 3I Atlas observations, professional astronomical meetings and publications remain notably quiet about preliminary results from the extensive observation campaigns that multiple space agencies have acknowledged conducting. This professional silence suggests institutional guidance that extends beyond simple administrative procedure into broader strategies for managing how major astronomical discoveries are revealed to scientific communities and general public awareness. The normal informal communication networks that typically spread exciting preliminary results through professional astronomy communities seem notably inactive regarding 3I Atlas observations. The contrast with historical patterns of major astronomical discovery reveals how significantly information management protocols have evolved in the modern era of space exploration. Previous encounters with unusual objects, from the first asteroid discoveries to recent interstellar visitor Oumuamua, generated immediate scientific discussion and public interest that paralleled the pace of observational data collection. But 3I Atlas observations seem managed according to more sophisticated frameworks that balance scientific revelation against other considerations that remain undefined in public communications. The institutional decision-making process that determines when observations should be shared and what level of analysis should precede public release operates according to criteria that aren't explicitly explained through normal channels. The global nature of the silence protocol becomes apparent when examining communications from multiple space agencies across different countries and political systems. The similar approaches to 3I Atlas information timing suggest coordination that extends beyond individual national space programs into broader international frameworks for managing significant astronomical discoveries. This international coordination indicates recognition that 3I Atlas observations carry implications that extend beyond routine scientific research into areas that may require careful consideration of broader social, political, or cultural impacts. The systematic approach to information management suggests awareness that immediate revelation of certain types of astronomical discoveries might generate consequences that careful timing and preparation could minimize or control. The technical sophistication of modern space missions creates opportunities for unprecedented levels of information control compared to previous eras of astronomical discovery. When observations occur through robotic platforms operating according to programmed schedules, the timing of information release becomes separated from the timing of data collection in ways that weren't possible during the era of purely terrestrial astronomy. This separation between observation and revelation creates opportunities for extended analysis, review, and preparation that can ensure information is released according to institutional priorities rather than natural discovery timelines. The silence protocol represents the systematic exploitation of these opportunities to manage how major astronomical discoveries unfold in public awareness. But the protocol also creates vulnerabilities that amateur investigators like Simeon Schmalz have begun to exploit. When raw data streams remain publicly accessible despite institutional reluctance to discuss preliminary analysis, opportunities exist for independent discovery that bypasses official information management entirely. The silence protocol surrounding 3I Atlas observations reveals institutional recognition that this interstellar visitor represents something more significant than routine astronomical discovery. The careful management of information timing and release suggests awareness that what has been observed during humanity's first close encounter with an alien visitor carries implications that extend far beyond typical space exploration achievements. The question that emerges from examining these institutional behavior patterns isn't whether significant discoveries have been made during 3I Atlas observations. The systematic application of silence protocols suggests they have. The question is what those discoveries reveal that requires such careful management of when and how they are shared with a world eager for answers about our first interstellar visitor. In the orbital mechanics of cosmic revelation, Mars occupies a unique position as humanity's witness to events that Earth cannot observe directly. During those crucial days in early October, as 3I Atlas made its closest approach to the red planet, sophisticated instruments positioned on and around Mars collected data that may represent the most significant astronomical observations of our generation. The question isn't whether extraordinary information was gathered. The technical capabilities and positioning ensure that it was. The question is what that information reveals about the nature of interstellar visitors and why such revelations seem to require careful institutional management before reaching public awareness. The totality of Mars-based observations creates a comprehensive dataset that spans multiple wavelengths, observation platforms, and analytical techniques. From high-resolution photography captured by orbital cameras to spectroscopic analysis conducted by specialized instruments, from surface-based atmospheric monitoring to detailed tracking of the object's trajectory and behavior patterns, the red planet's mechanical inhabitants have documented 3I Atlas with unprecedented thoroughness and precision. This observational completeness provides opportunities for understanding interstellar visitor characteristics that no previous encounter has achieved. Unlike brief flyby missions or limited Earth-based telescope observations, the Mars platform enabled extended monitoring of 3I Atlas behavior over multiple days, tracking changes in activity patterns, documenting structural characteristics at close range, and analyzing the chemical signatures of materials that originated in alien stellar systems. The proximity advantages of Mars-based observation translated into data quality improvements that likely exceed Earth-based capabilities by factors of 10 or more. Resolution, signal-to-noise ratios, spectral analysis precision, and temporal coverage all favor the Martian observation platform significantly. This means that the most detailed and scientifically valuable information about humanity's first close encounter with an interstellar visitor exists within datasets collected by instruments positioned on and around the red planet. But the synthesis of this observational wealth reveals patterns that challenge existing frameworks for understanding what interstellar objects should look like and how they should behave when they encounter alien solar systems. The accumulated evidence from Mars-based observation suggests an object that defies easy categorization within established astronomical taxonomy, while providing unprecedented insights into stellar formation processes that occur under conditions different from those in our solar neighborhood. The structural characteristics documented through high-resolution Mars-based imagery reveal an interstellar visitor with organizational complexity that exceeds expectations for typical cometary objects. Instead of the loose agglomeration of ice and dust that characterizes most solar system comets, 3I Atlas displays structural integrity and surface features that suggest formation processes or evolutionary history significantly different from objects that originated within our stellar neighborhood. The chemical signatures detected through spectroscopic analysis from Mars platforms provide direct observational evidence of stellar chemistry and planetary formation dynamics that operated under conditions unlike those that created our solar system. The elemental abundances, molecular structures, and isotopic ratios observed in 3I Atlas materials carry information about the stellar environment where this object formed, potentially billions of years ago in a stellar system with different metallicity, radiation characteristics, or evolutionary history than our own. The activity patterns documented as 3I Atlas responded to increasing solar radiation reveal behavioral characteristics that don't match standard models of cometary evolution. The timing, intensity, and spectral properties of gas releases suggest internal composition and thermal properties that indicate formation under stellar conditions that may not exist in systems similar to our own. Understanding what type of stellar environment could produce such characteristics requires extending theoretical models beyond the relatively narrow range of conditions represented by our solar system's formation history. The magnetic field interactions detected as 3I at LUS moved through the solar wind provide evidence of internal structure that includes metallic or electrically conductive materials distributed in ways that create detectable electromagnetic responses. These magnetic properties have important implications for understanding how interstellar objects navigate galactic magnetic fields during their journeys between stellar systems, and the likelihood of multiple visits from objects originating in particular distant stellar regions. The density measurements and thermal characteristics inferred from Mars-based observations reveal an object with mass distribution and heat transfer properties that suggest material compositions or structural arrangements that differ from both typical comets and typical asteroids. This intermediate character indicates formation processes that may occur in stellar systems with different evolutionary histories, different chemical abundances, or different environmental conditions than those that created objects within our solar neighborhood. But perhaps most significantly, the totality of Mars-based observations provides evidence that 3I at LUS represents something more complex and scientifically significant than a simple chunk of interstellar ice and rock. The accumulated data suggests an object that carries within its structure direct observational evidence of stellar chemistry, planetary formation dynamics, and cosmic evolution processes that extend our understanding of how material formation and development proceed throughout the galaxy. The implications of these Mars-based observations extend far beyond the immediate study of one interstellar visitor. 3I at LUS becomes a traveling laboratory, carrying experimental results from alien stellar chemistry across interstellar distances, providing crucial calibration data for theories of cosmic evolution and planetary formation that were previously based only on observations of our local stellar environment. Understanding how materials formed under different stellar conditions behave when they encounter our solar system's radiation environment provides essential information for interpreting future interstellar visitor encounters and developing more sophisticated theoretical models of galactic chemical evolution. The data collected during 3I at LUS's passage past Mars will likely influence astronomical research and theoretical development for decades to come. Yet this potentially revolutionary information remains largely inaccessible to scientific analysis and public understanding due to institutional decisions about information timing and release protocols. The most detailed spectroscopic analyses, the highest resolution structural imagery, and the most comprehensive behavioral documentation exist within datasets that may not be fully shared for months or years after collection. The synthesis of Mars-based observations reveals that humanity's first close encounter with an interstellar visitor has provided unprecedented insights into stellar formation processes, galactic chemical evolution, and the diversity of planetary formation dynamics that occur throughout cosmic history. 3I at LUS carries within its structure direct evidence of how cosmic evolution proceeds under conditions different from those in our solar neighborhood, offering observational data that extends our understanding of universal processes far beyond local experience. But accessing these insights, understanding their implications for theories of cosmic evolution and galactic development, and incorporating them into improved models of stellar system formation throughout the universe, requires information sharing that prioritizes scientific discovery over administrative procedure, natural curiosity over institutional control. What Mars saw during those crucial October days represents more than just successful observation of an unusual cosmic object. It represents humanity's first direct encounter with materials and formation processes from alien stellar systems, carrying implications for our understanding of cosmic evolution, galactic chemical development, and the fundamental processes that govern how matter and energy organize themselves throughout the universe. The red planet's mechanical witnesses have documented phenomena that challenge existing theoretical frameworks while providing observational data that could revolutionize astronomical understanding of stellar formation, planetary development, and cosmic evolution processes that extend far beyond our immediate stellar neighborhood. The question isn't whether extraordinary discoveries have been made. The accumulated evidence suggests they have. The question is when those discoveries will be shared with a world ready to expand its understanding of cosmic processes that connect our solar system to the broader universe of stellar formation and galactic evolution. As November progresses, and 3I at LUS continues its departure from the inner solar system, the interstellar visitor begins to fade from direct observational capability, disappearing behind the bulk of our Sun as viewed from Earth. and becoming increasingly difficult to detect, even from the advantageous positions of Mars-based instruments. This cosmic vanishing act creates a natural endpoint to humanity's first extended encounter with a visitor from another stellar system. But the implications of what was observed during those crucial months continue to reverberate through astronomical research and theoretical understanding in ways that will influence cosmic science for decades to come. The physics of 3I Atlas's departure follows the same gravitational laws that governed its approach. But the observational challenges multiply as distance increases and solar interference blocks Earth-based detection capabilities. The object that once appeared as a faint but detectable enhancement in processed imagery now fades below the threshold of reliable observation, carrying its secrets back toward the interstellar void from which it emerged. Yet the disappearance of direct observational capability doesn't diminish the significance of what was documented during the interstellar visitor's passage through our solar system. The datasets collected by Mars-based instruments, the spectroscopic analyses conducted during peak activity periods, and the behavioral documentation gathered over months of systematic observation represent a treasure trove of information about stellar formation processes and cosmic evolution that extends far beyond our local stellar neighborhood. The lasting impact of 3I Atlas observations will unfold gradually as researchers gain access to complete datasets and begin the extended process of analysis, interpretation, and theoretical integration that transforms raw observational data into improved understanding of universal processes. The chemical signatures detected in interstellar materials will provide calibration data for models of stellar formation throughout the galaxy. The structural characteristics documented through high-resolution imagery will influence theories of planetary system development under different stellar conditions. The behavioral patterns observed during solar heating will refine understanding of how objects formed in alien stellar environments respond to radiation conditions they've never previously encountered. But perhaps most significantly, the institutional response to 3I Atlas observations has revealed patterns of information management that suggest recognition of discoveries more profound than routine astronomical findings. The systematic application of extended review periods, the coordination between multiple space agencies regarding information timing, and the careful management of revelation schedules all point toward institutional awareness that what was observed carries implications extending beyond typical space exploration achievements. This recognition creates both opportunities and challenges for the future development of interstellar visitor research. On one hand, the institutional attention devoted to 3I Atlas observations suggests commitment to thorough analysis and careful interpretation of potentially revolutionary discoveries. The extended review periods may ensure that preliminary findings receive appropriate verification and that theoretical implications are carefully considered before public revelation. On the other hand, the systematic delays in information sharing create frustration within scientific communities eager to begin independent analysis of potentially groundbreaking observational data. The same institutional caution that ensures careful verification also prevents the rapid collaborative investigation that typically accelerates understanding of major astronomical discoveries. The amateur astronomy communities that provided some of the first independent confirmation of 3I Atlas detection from Mars demonstrate the evolving relationship between institutional control and democratic access to space exploration data. The technical capabilities that enable sophisticated robotic missions also create opportunities for independent investigators to participate directly in the discovery process, sometimes achieving results that parallel or exceed official institutional analysis. This democratization of space exploration discovery suggests that future interstellar visitor encounters may unfold according to different patterns than the carefully managed revelation that has characterized 3I Atlas observations. As analytical tools become more sophisticated and data streams become more accessible, opportunities multiply for significant discoveries to emerge through independent investigation rather than institutional revelation. The precedent established by 3I Atlas observations will likely influence how space agencies approach future encounters with unusual or potentially significant objects. The institutional frameworks developed for managing information about humanity's first close encounter with an interstellar visitor may become standard protocols for discoveries that carry implications extending beyond routine astronomical research. But the precedent also demonstrates the limitations of information control strategies in an era of increasingly sophisticated amateur investigation capabilities. The same technological infrastructure that enables institutional data collection also enables independent analysis by individuals and communities with sufficient technical expertise and determination to extract meaningful results from publicly available information streams. The disappearance of 3I at Lus behind the Sun creates a natural pause in direct observational capability, but the scientific impact of its visit will continue expanding for years to come. The datasets collected during its passage represent humanity's first comprehensive analysis of materials and formation processes from alien stellar systems, providing observational evidence that will influence theoretical development across multiple fields of astronomical research. The chemical analyses will inform models of stellar nucleosynthesis and planetary formation under different stellar conditions. The structural documentation will guide theories of object formation and evolution in diverse galactic environments. The behavioral observations will refine understanding of how interstellar materials respond to radiation environments they haven't previously encountered. Most importantly, the successful observation of 3I at Lus demonstrates humanity's capability to conduct sophisticated analysis of interstellar visitors when they enter our solar system. The technical infrastructure, analytical methods, and institutional coordination developed for studying this first close encounter create frameworks that will enable even more comprehensive analysis of future visitors. The vanishing act of 3I at Lus marks the end of direct observation, but the beginning of extended analysis that will gradually reveal the full significance of humanity's first close encounter with a visitor from another stellar system. The implications of what was observed will continue expanding as researchers gain access to complete datasets and begin the process of integrating interstellar visitor characteristics into broader theoretical frameworks of cosmic evolution and galactic development. As 3I at Lus fades into the cosmic background, disappearing back into the interstellar void from which it emerged, it leaves behind datasets that may revolutionize our understanding of stellar formation processes, planetary system development, and cosmic evolution throughout the galaxy. The temporary visitor has become a permanent expansion of human knowledge about the universe beyond our immediate stellar neighborhood. The question isn't whether 3I at Lus provided revolutionary insights into cosmic processes that extend far beyond our solar system. The accumulated observational evidence suggests it did. The question is how quickly those insights will be shared with scientific communities and general public awareness, and whether the institutional frameworks developed for managing this first interstellar encounter will facilitate or constrain the collaborative investigation that typically accelerates major astronomical discoveries. The cosmic vanishing act of 3I at Lus creates both an ending and a beginning, the end of direct observational opportunity, and the beginning of extended analysis that will gradually reveal what humanity learned during its first close encounter with materials and formation processes from alien stellar systems. The interstellar visitor has returned to the void, but its legacy in expanded human understanding of cosmic evolution will continue growing for decades to come.